So, impulse. We're going to talk about impulse. This looks like Gympulse. I'll change that. Impulse, the variable is j. Okay, we talk about momentum having a variable that we defined as p, and impulse is the change in momentum. And usually the momentum can change because you pushed on something or you pushed against something, but really a change in momentum, or j, impulse we say, change momentum, it's the same thing as saying the final momentum minus the initial momentum. And we've talked about what momentum is before. It would be mv2 minus mv1. It's a vector calculation. We also talked before about how change in momentum relates to Newton's second law. And actually maybe even Newton would have said it this way. Instead of saying F equals ma, you'd be likely to say something along the lines of m times v2 minus v1 all over delta t, which would end up being mv2 minus mv1 all over delta t. And you can see I've drawn these side by side. I've written these side by side, so you can see the side by side comparison. That this bit here and this bit here is the same thing. And so it's entirely possible that Newton might say, instead of F equals ma, F equals mv2 minus mv1 all over delta t. Or he might have just said that his second law was equal to change in momentum over time. Or he could have just said impulse over time. All equivalent statements. Okay? So impulse doesn't necessarily make things more complicated. It's actually just a description of a change of momentum. Now if I had, I want to choose a scenario. Oh, you know what, before we do, some people may be interested in saying instead of just F equals delta P over delta T, sometimes people don't like to have it as a denominator, or a scenario with a denominator. Oh shoot. I've just frozen up there. Some people don't like to have a denominator when they write F equals delta P over delta T. So you will see from time to time that people say that the change in momentum, or P, is equal to force times delta T. And actually that crops up when you're doing graphing problems. So for example, if you have a graph that's a force versus time graph, for example, and people want to know, well, what's the impulse for a graph that looks something like this? Well, since change in momentum is force times delta t, change in momentum, or impulse, would just be the area under this graph. And so we could break it up into some geometric shapes, find the area underneath of the graph, and that would tell us what the change in momentum is for the object. Now the graph isn't always a nice geometrically shaped graph like this. Sometimes we get some curvilinearly shaped graphs, like this one for example. Force times time. And maybe you get a graph that looks something like this. So force varies as time goes along. We push harder and harder and harder, but it maybe plateaus off after a little while. Say, well, how do you figure out the area under that graph? Well, I'll give you a little bit of a tip, because this will show up in homework and things. Something that people have done for years, especially preceding calculus, is to take graphs like this and break them up into bar graphs. And if I want to find the area under a graph like this, for the horizontal portions it's not so bad. I could just calculate the area of this rectangle if I knew the width and the height of it. But when I get to portions like this one here, you'll notice what I've tried to do is make this little triangle that I've neglected be around the same area as this little triangle that I included. And so if I can use a bar graph like this, it's a way to approximate the area underneath of a curve without somehow coming up with an equation for the curve itself. You can break it up into bar graphs. And people that are really keen on limits might notice, if you do enough of these, that the narrower you make the bars, the more accurate your calculations are going to end up being. And so you make more and more calculations for the rectangles, and people will notice, if you've done the calculus course, you'll say, oh, that sounds like an application of limits. Well, it is an application of limit. In the limit, where you make this we'll call it delta x, the width of the bars reach or approach 0, you're going to be more accurate. Okay? So I want to just throw that out there as a little bit of background information, but I want to move on from there. I want to say, well, what if I had, this is the motion of an ant. Maybe it's an uncle. I'm not quite sure. If you take a magnifying glass, you can check or ask politely. At the beginning, we know that we could figure out what the velocity is. V2. Or it's V1 rather, V1. We could figure out what the velocity is. Maybe we use some sort of a stop frame camera to figure out how much time it takes between shots, and we could calculate what the velocity is. And we've done activities with that sort of thing previous in the course, and we could figure out what the final velocity is, no problem. We could, I guess my point is, we could, well, let's throw out some reasonable values. Let's say that this ant travels along at the beginning at 0.200 meters per second. 2 centimeters per second, which is a pretty awesome clip for an ant. That's really fast. Well, maybe it's not the fastest, but it's pretty quick. And then sometime later, let's say that it slows down to being about a third of that, 0.00700 meters per second, 7 millimeters per second. Okay, so we're going to slow it down a little bit. And let's say that the mass of the ant, actually, maybe we should have a reference frame here too. Let's say that the ant is moving to the right, and so we're going to make the right positive, and we'll make the left negative. And maybe we should define our points as well. Let's say that the ant goes from position A to position B. It's actually getting to be a lot of information here for this little ant. I should give some directions for my vectors as well. Okay, so to the right, the ant is always moving. Let's give a reasonable mass for the ant. So my ant, actually, do you want to use a African ant or a common American ant? African ant? Okay. Then as everybody knows, an African ant has a mass of, on average, 0.00153 kilograms. You guys knew that, right?
Of course.
Yeah.
Good. Come in! Hello?
We're collecting for Tuning Tuesday.
What is Tuning Tuesday?
Okay, we're going to pause it just there.
It's for schools and bank